Hello everyone, and welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. Sometimes it may happen that we may want to use a microcontroller board to create a measurement device, either directly with an LCD screen or perhaps just measure some voltages and send them via, I don't know, HTTP or something, Wi-Fi, Bluetooth. In that case, we will basically need to use the ADC inputs of that particular microcontroller. However, then we might get into a bit of a problem that we might want to fix somehow. The problem is basically the power supply voltage. If we power this device from a switch mode power supply, which is basically the easiest and cheapest way, especially since these boards need 5 volts, and we can basically use any old phone charger or tablet charger, well then the accuracy of our ADC readings will be influenced by how smooth this power supply voltage is. The more ripple we will have on the power supply, the bigger problems we will have with our ADC. And let's take a look at this in order to better understand what we're talking about. Okay, so let's say we have a 5 volt power supply, like I said, the phone charger that we don't use anymore. And we are using that to power, I don't know, an Arduino board or a Raspberry Pico or something. If we don't provide a reference voltage for the ADC that's separate from the power supply, which tends to complicate our design, then our microcontroller will use the power supply herself to take as a reference voltage, and therefore whatever fluctuations we have on the power supply will be reflected on each reading of the ADC inputs. So let's say we have this waveform. With blue we have something that looks like an inverse sawtooth. This is how one particular power supply that I have here in the lab looks like. It's a 10 amp power supply, and at very small currents I have about 80 millivolts of ripple. Now that might not mean like a lot, however, relative to 5 volts or to 3.3 volts depending on a case, that might mean quite a significant amount. So an Arduino has a 10-bit ADC and the Arduino board is powered directly from 5 volts. So an 80 millivolt ripple relative to 5 volts mean 1.6% error. A Raspberry Pi Pico has a 12-bit ADC and is powered from a 3.3 volt voltage. The board has a step-down converter from 5 to 3.3 volts. So 80 millivolts of ripple relative to 3.3 volts, that would be 2.4% error. This can be significant. So if we care about having a better accuracy for our readings, then we need to solve this problem somehow. Like I said, one possible solution is to use the analogic reference pin to input a separate, very stable voltage, but then we would need to create this voltage in the first place. We would need to have a dedicated portion of our entire circuit that does just that, just generates a reference voltage. And you know, sometimes we don't want to complicate ourselves. So a simpler solution would be to use a low dropout voltage regulator to power our microcontroller boards. And this is what I will want to talk about briefly in today's video. I will want to, well, I wanted to take a look at 3 of the cheapest low dropout integrated circuits on the market and see how well they behave, what's their performance, and you know, can we use or can we not use them in such projects. So the idea is to basically search for a power supply that gives more than 5 volt on the output, let's say 5.2, 5.3 volts, and these should be relatively easy to find, because if we take old phone chargers or battery chargers and we actually test them, we will see that they don't really give 5 volts sharp. They all are always a little bit above 5 volts or a little bit below 5 volts. So if we take a 5 volt, more than 5 volt power supply, we could potentially use a low dropout regulator to set the output voltage to 5 volts. And if the regulator has very, very low dropouts, like in the order of 100 millivolts or so, then this problem will be solved. On the output, we will have a smooth voltage to feed our microcontroller boards. So this is what we will be looking at. I have chosen 3 low dropout regulator from the market to take a look at them, see how well they perform. I have chosen the 3 cheapest low dropout regulators that I could find here in my country. I'm not saying these are the only ones, I'm saying these are just my choices. 2 of them from Diodes Incorporated and 1 from Texas Instruments. So we have model AP2202 that comes in multiple fixed voltage versions, but also in one that is adjustable. Okay, this model appears to be in a pretty good stock, over 1,800 pieces right now on this supplier only, and 100 pieces cost only 18 euros, so basically they cost 11 cents per piece, which is pretty cheap, I would say. Another model from Diodes Incorporated, AP2127. Again, I chose the adjustable version because they have multiple fixed voltage versions. This is even cheaper, it's just 6 cents per piece at 100 pieces bought, and 1,400, more than 1,400 pieces in stock. So it shouldn't be a problem acquiring this. And the last version was TPS79301, which is the adjustable version. The fixed voltage versions have something else other than 01 after 793. Anyway, this model is from Texas Instruments, and it's significantly more expensive, 35 cents per piece at 100 pieces. But exists in even larger quantity, over 5,600 pieces in stock right now. Now, it is true that this particular distributor gives us a warning that apparently this model of chip is hard to obtain. So I'm guessing, you know, the production is not so good right now, but I don't think these 5,600 pieces will go out of stock anywhere soon. So I'm pretty confident to add this model on the list. All three of these chips come in SOT23 packages, and it is true that they are going to be a little bit of a pain in the ass to solder them on a board. It's not impossible, but they're gonna be a little bit more challenging to solder them on a board. However, if you don't want to do that, there's an alternative, which is to use the sponsor of this video, which is PCBWay, leading PCB manufacturer that can help you build your dream projects, no matter how advanced they are. You can place an order for them to solder these chips on boards and deliver the boards already with components placed on them, so you don't have to bother with soldering such small components. They can create just the PCBs for you or help you solder components, like I said, through PCB assembly services. If you're creating a full device, they can also help you create a plastic case through either 3D printing or injection molding services, or even CNC machining if you need custom metal pieces for a metallic case. You're free to use your favorite design software, upload the Gerber files, and one of their professional representatives will contact you, offering you one-on-one customer service. All you need to do is go to PCBWay.com. The link is in the description. Thank you very much, PCBWay, for sponsoring another video. And now let's move over to testing these low dropout regulators and see how well they perform. So as far as the tests goes, I basically created some circuits that are pretty close to what each datasheet recommended. I basically, these are very simple chips to use, very simple integrated circuits to use. We just need a filtering capacitor on the input. I chose a 1 microfarad one. A filtering capacitor on the output. I chose 10 microfarad ones. We need to use a voltage divider to set, for the feedback pin, to set the output voltage. And I chose to put a semi-adjustable 10 kilo ohm potentiometer. And in the case of the Texas Instrument model, this one comes in a 6-pin package. One pin is recommended to be connected to a 10 nanofarad capacitor for extra filtering, and this needs to be connected to the ground on the other side, which is what I did. And this is pretty much it. We don't need to use anything more than that. And of course, I have used various resistors as loads. Okay, and now I have used different resistors to pull different amounts of current, and I have taken a look at the input voltage ripple and then the output voltage ripple. I have performed adjustments to see how big the dropout between the input and the output is, in order for me to have a nice smooth voltage on the output. And I have compiled basically a table of results. So let me show you step by step each let me show you step by step each tests performed. I have tested all of them with a 50 milliamp output current. because a typical microcontroller board consumes, at least one that does not have Wi-Fi or Bluetooth enabled, consumes roughly, well, between 20 and 50 milliamps. So I decided to test the dropout of every regulator basically at 50 milliamps. And then I decided to test a higher current, and this depended on every chip, because every chip can output different amounts of currents. Okay, so now AP2202, what I did is basically adjust the output voltage so that the chip cannot regulate. Like we have here, with blue we have the input voltage, with yellow we have the output voltage, and then I adjusted the output voltage so that the chip does regulate and gives me a nice smooth straight line on the output, okay, without ripple, without anything else. And then I basically measured the input voltage with a voltmeter. I wrote that number down in the table, and then I connected the voltmeter to the output and measured the output voltage. The difference is the so-called dropout. Okay, so this is at 50 milliamps. It's a dropout from 4.90 something volts all the way to 4.70 something volts, so 200 millivolts. Okay, for 100 milliamps, the same chip, but 100 milliamps of current, I performed the same operation. So here we have both channels coupled AC, 20 millivolts per division, in order to take a look only at the ripple. Okay. And then, you know, taking a look at the voltages. On the input, we have 4.87 on the input, and then on the output, we have 4.5152 volts. Okay. Then, moving on, AP2127 chip. This one can withstand 300 milliamps on output. So this is the first test with 50 milliamps. Okay. Input voltage 4.9293. Output voltage 4.8182. And this happened to be the smallest dropout voltage of them all. And then drawing 250 milliamps current on the output, because again this chip can officially provide 300 milliamps, so I chose to test him with 50 milliamps less than the absolute maximum. 4.69 volts on the input, and then on the output 4.2 volts. Last chip, the Texas Instrument one with 50 milliamps. The same test. On the input we have some 4.93 volts. On the output 4.76. And with 150 milliamps, because this chip can withstand 200 milliamp output current. So 50 milliamps less than the maximum permissible current is 4.7778 volts on the input and 4.3132 volts on the output. Okay, so now taking all of these values and putting them in a nice table, we can clearly see that at least for drawing 50 milliamps, AP2127 is the best. Has only a 110 millivolts of dropout voltage, followed by the Texas Instruments one, 170 millivolts dropout voltage, and last is AP2202, which has 200 millivolts of dropout voltage. Then at maximum current minus 50 milliamps, things are a bit different. Now, of course, since these are different currents, we cannot really compare them side by side, but I would say they behave pretty much the same. At 100 milliamps, which is 50 milliamps less than the maximum current, AP2202 needs 360 millivolts of dropout voltage in order to perform regulation. At 250 milliamps, which is again 50 milliamps less than the absolute maximum current, AP2127 needs almost half a volt to perform regulation. And the Texas Instruments one at 150 milliamps needs 460 millivolts dropout voltage in order to give us a good performance. So this is pretty much it. There's nothing else to be shown or said. This was a shorter video than usual. I needed this because I'm basically wanting to use a Raspberry Pico and an LCD screen for a project that I will show you the next days. Hopefully I will finish him this month. I want to create a device that is able to measure the active power and the apparent power of AC devices in our house, you know, ranging from very small laptop chargers, phone chargers, all the way up to, I don't know, electric stoves, electric ovens, any consumer in between. We will want to measure how much active power they draw and what's their power factor in order to, you know, better assess what kind of inverters we need. And for that I will use Raspberry Pico. And basically, in order to obtain, you know, nice, accurate results, I need to smooth the power supply rails with such an LDO that I have shown you in this video. So that's pretty much it. I hope you found this video useful. Stay tuned if you want to see this device being built. Thank you very much for watching. Thank you very much also to the supporters of this channel. There's a Patreon link in the description for those who want to support this channel financially. Otherwise, a subscribe and a like is free and helps the YouTube algorithm promote my videos to other people who might be interested. Again, thank you very much for watching. I will see you soon. Bye bye.